All right, let's go.
All right, good morning. This is our trust final project. My name is Christian Burns.
My name is Victor Olawipo.
My name is Stephen. We have Fam Markle.
And I'm Gabriel Chivari.
Let me start off by going through our truss design. So truss is the construction of triangles in shapes because it's the strongest shape. They use them in buildings to help with like stability and strength. So this was our design. We have an 8-member truss with 6 joints, and we have them assigned from like bottom to top. So it'd be A is down in the bottom left, B is in the middle, C, then we have D, E, and F. So our truss is money themed for our trust name, which was Trust Fund Baby. Um, so I personally took the truss home and we painted it green, and then we put some dollar signs on each member, and then we also added some dollar bills to each gusset plate. So the actual construction of the truss went fairly well. I didn't notice any major hiccups when we were constructing the truss. The only main problem that we had is that another team accidentally used our members. So we actually had to get our members cut again in the wood shop, but which was no big deal. Just had to get them cut again. Everything was constructed well. The only major flaw that I would say we had that something we could improve upon for the future was our bottom surface wasn't exactly flush. So I think gusset plate A was like a little slightly lower. And so when the weight was applied to our truss, it was a little bit unbalanced. So that way our truss actually failed at point A. And I think this was because of the uneven distribution of weight to that point. And so in the future, we would try to minimize that by making everything flush on that bottom surface. But outside of that, I think the truss construction went very well. Uh, no major flaws. And so now I can move on and we can talk about the actual failure point of our truss.
So the maximum failure load was 404 pounds, and it failed due to shear failure at joint A, and estimating the failure we estimated incorrectly with a percent error of 309%, and that was mainly caused by miscalculations in shear failure, where the area was overestimated. Furthermore, there was a little bit of errors in constructing the truss, um, which contributed to the premature failure and the overestimate of the failure prediction. Next slide. So, as you can see on the diagram, the truss failed at point A. We predicted the truss to fail at point C due to shear, and while the failure method was consistent, the failure location and the amount of force required for failure was skewed. And again, that was mainly due to errors in shear calculation and errors in construction. Excellent.
Yo, Gabe, you're muted, bro.
Sorry. So across the class, there is a consistent prediction of load capacity. Most teams predicted failure of loads around 800 to 2,000 pounds, while actual failure clustered much closer to 100 to 600 pounds. This suggested that many of the designs did not fail by pure axial member capacity, as assumed in the analysis, but instead due to buckling due to buckling and compression of members, or joint failure, or unaccounted eccentric loading, and just construction imperfections overall. The best performer was Group 17 with a predicted load of 650 and an actual one of 750, which could be due to a conservative analysis and just efficient load pass. Some other strong performers were Group 1 and 13, who each got 587 pounds and 570 respectively. And the worst performers were groups 5 and 8 with 112 pounds. with a predicted of 1,700 pounds. So we're tied for lowest. These represent the largest prediction of performance gap. Some likely failure causes could be like the slender compression members, or just weak joints and optimistic assumptions overall. It Group 14 had a major overprediction with a prediction of 2,000 pounds, which was the highest prediction in the class, with an actual load capacity of 200. This indicates theoretical strength was not achieved due to instability or construction limitations. Some notable outliers were Group 6, which predicted it 1901 pounds and failed at 259. So strong overestimation at Group 9 with a very low prediction of 445 and missing failure data. And then there was Group 10 and 12 with mid-range and relatively consistent, but still overpredicted. It was a pattern across most groups to overpredict, and that's just a matter of imperfections in the actual construction process. Uh, our group predicted a load of 1,600 and failed at 404. It We stack up in comparison to the class above average in actual failure load and performed better than many teams with similar or higher predictions. Um, Comparable to mid upper performers like group 7, 10, and 12. Our group did not reach top tier performance, but was solidly competitive, and we could have done a lot better if it weren't for essentially our plate exploding and it like tipped over. It so yeah.
So, what did we take away from this project? We learned a lot of things. Number one, I would say one of the things that we learned is to improve our calculation. So, during our project, we actually like when it came to our actual failure load compared to our predicted should have been way closer to our actual calculation, which we calculated, I believe, because we added some of our calculations instead of multiplying. So we would have been one of the closest in the class to our predicted value, but that was just an error that we'll look at for in the future. And then also when analyzing our trust results, like one key metric was the percent error. So it tells us like how our actual max load deviated from our actual predicted, our actual theoretical prediction. And now in theory, like our calculations, they assume like perfect materials, perfect joints, no human error. But in reality, that plays a huge factor in the way that we built our trust. So like simple things like uneven cuts, like the glue being off center, or just like minor joint misalignments, they can lead to early failures and lower strength than expected. Like my group mates mentioned before, how the gusset plate exploded first rather than um the middle member CD actually failing. That showed that we had a good stability there. However, like at the bottom gusset plates at the bottom left and the bottom right of our truss, they weren't stabilized at the testing site, so that could have made our truss last longer than it should have, but it actually did not last as long as we wanted it to. And in practice, we also think that when we talk about like the truss height, a lot of us assume that taller equals stronger. So like while like a greater height, it can reduce like internal forces. That only helps if the truss is well built and stabilized and perfect throughout, as I mentioned before. So in practice, like taller trusses, they can buckle more easily and they're harder to assemble on a more accurate basis. So like more height, it doesn't always mean better results, but especially if its build quality is compromised at certain points in the truss. So our percent error wasn't just about the math; it reflected like the real world imperfections. So it reminds us that engineering success depends like just as much on your execution as it does on your design. So yeah, those are some of the things that we learned from our project.
Yeah, so I can add on to that a little bit. Um, I like how Steven said that we are doing our calculations based off of perfect results. which is true, and this is why our results may be a little bit off because oftentimes if that joint is shifted over just a centimeter or two on the gusset plate, because there is room for that, that could completely shift your calculations. Similarly, if there's more glue on one joint versus less glue, or things of this manner, can always reflect different results. So I think that's why there was a big disparity of people's actual guesses to what their trust would do versus what they actually performed in. And so that's just kind of like a big example of engineering as a whole because our calculations can be correct, but we also have to have errors and we have to account for those because if something like this happened in the real world, where a truss failed 2,000 pounds less where than it was supposed to, like this can be like a big error in the world. So it's a kind of some good lessons that we learned. But that'll complete our project. Thank you for listening, and I hope you guys have a great day.